Hello there and welcome back. In this video we're going to be focusing on object counting and rearrangements of objects, whether they be distinct or not. So let's begin with a very easy to understand scenario. Let us assume S is a set that contains little n objects. And let's also assume that this little n is of course a natural number, so that's what that fancy n represents. So 1, 2, 3, 4, 5 million or even higher. And this very important word, distinct, means they are all different from each other. Therefore, you don't have any repetition of these objects, and you can sort of see the difference between each of them. So let's assume you choose one, exactly one, of these n objects, and let's give it a name. Let's call that object x. And let us also assume that we do not replace it. Then, how many objects are left? Well, that means there are going to be n minus 1 distinct objects left in this particular set S. So that's a starting point. So the next principle, which is called the fundamental counting principle, and some people will refer to it as just FCP for short, is going to be very fundamental in a lot of these counting strategies that we're going to actually be looking into today. So let us now choose another object from this data set S, and let's call it Y, and let's consider the set of all possible pairs x comma y, where x is the very first element and y is the second element that is drawn, and let's assume that we do not replace the first. So the guiding question here is, how many elements are in R? So how many distinct pairs are in the set R? So the fundamental counting principle says that the number of elements in the set R is going to be equal to, well, if we focus on the very first element, how many elements could it have been? Well, there was n distinct objects in the set originally, therefore there should be n possible choices for x. Well, how many possible choices are there for the second element? Well, that's going to be n minus 1. And the fundamental counting principle says the number of objects in this set R, or the number of distinguishable pairs x comma y, is actually just going to be equal to n times n minus 1. So let's look at a very basic example to sort of see how that looks in the real world. So let's look at a very basic set. Let's consider the set S, which contains the distinct elements A, B, C, D, and E. And let's choose 2 without replacement. So what are all the elements in this set R? So we're going to choose one, and then we're going to choose another without replacing the first, right? So we could get A, B, we could get A, C, we could get A, D, we could also get A, E. In addition, we could get B, C, B, D, B, E. We could also get C, D, C, E, and we could also get D, E. Is there any more elements that we are missing? Yes, the mirror images of them. So we could get B on the first and A on the second. We could get CA, DA, EA, CB, DB, EB, DC, EC, and ED. So is that all the possible pairs? The answer is yes. But one may ask, well, what if I'm missing any? So originally there are 5 elements in this set. So that means by the fundamental counting principle, there's going to be 5 times 5 minus 1, which is of course 5 times 4, which is equal to 20. And this of course gives me how many elements that I have listed in this set above. So that's just a very basic example of the fundamental counting principle. Now the question becomes, well, if we can choose 2 objects without replacement, is it possible to select more? And of course the answer is yes. So for example, if we have a set of 5 objects, and let's assume that they're all distinct without replacement, then I could choose 3, I could choose 4, and I could choose at most 5 of them. So is it possible that we can extend this result to selecting, say, k objects from this set? So let's see if we can generalize that to the more general form. Alright, so let's suppose that the size of S is equal to n, and let's assume that this is n distinct objects, and you choose k of them, where, of course, k must be greater than or equal to 0, and k should be less than or equal to m. And let's assume this choice is without replacement again. So how many object pairs can we have now that are distinguishable? So we're going to have n for the first draw, we're going to have n minus 1 for the second, we're going to have n minus 2 for the third, we're going to have n minus 3 for the fourth, and so on, all the way down to the last kth draw. Now let's see if we can figure out what this pattern is going to be. So this is the first, this is the second, this is the third, this is the fourth. Now what's the relationship between the selection index and this particular number that we're subtracting? So that is negative 2 plus 1, that is negative 3 plus 1, so that's negative 4 plus 1. So if we continue this all the way down to the kth draw, so that should be minus k plus 1. Now minus k plus 1 doesn't simplify, like minus 4 plus 1 is negative 3 and minus 3 plus 1 is negative 2, so we just leave it as so. So that's going to be equal to n minus k plus 1, and that is the general extension. Now that might be a little bit more complicated to remember, so maybe we can play around with this expression algebraically and get something that is a little bit more useful. So let's write that again. So the size of r is going to be equal to n times m minus 1 times m minus 2 all the way down to m minus k plus 1. And if we continue this downwards, let's actually continue on. So n minus k plus 0, and then it's going to be m minus k minus 1, m minus k minus 2, all the way down to 2 times 1. Now that numerator should look familiar because that's precisely kn factorial, right? So on the bottom, since we introduced this blue thing, if we do something to the top of this fraction, we have to do the same to the denominator as well in order to keep this fraction equivalent. So that's going to be equal to m minus k times m minus k minus 1, m minus k minus 1, m minus k minus 2, all the way down to 2 times 1, and that's precisely equal to m minus k, the quantity, factorial. So therefore, we have a nice condensed representation for this. So the number of rearrangements of choosing k objects from n distinct objects without replacement is going to be equal to n factorial divided by m minus k, the quantity, factorial, and this does sometimes have another name. This is actually called a permutation. But this is the general formula for that particular problem. Now I also need to make a quick note here. Remember when we were selecting those two objects from that set with the letters A, B, C, and D? Remember we were treating the pair AB and the pair BA as different pairs. That means these two things are not equal to each other. That's going to be very important because one may ask, well, aren't they the same letters? Yes. So maybe you want to count them as equal and not double count them. That would be another type of strategy, which we will definitely look into. But before we get into that, let's ask another very basic question. What if we have replacement? So can we do this with replacement? The answer is yes. So let's figure that out. So how many objects do we have for the first draw? We're going to have m. Once we draw that, we're going to put it back into the set. So once we draw it, we have n minus 1. Once we put it back in, we have n. So there's going to be n objects for the second draw, n objects for the third, all the way down to the number of draws that we have, which is still going to be equal to m. So if we're drawing n or k objects, we're going to have n to the power of k. So that's the with replacement variation of this. So now that we've looked at a finite set with distinct elements in it, and we can also choose k of them with and without replacement, now the question becomes, well, what if you have repetition in that particular set? How can you count all the distinct rearrangements of those objects, whether we select all of them or a subset of them? So let's see if we can answer that question with minimal difficulty. So what if there is repetition? All right, so let's consider a guiding example. Let's consider the set S, which is going to be equal to the set A, B, B, C, 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 and C. So how many objects do we have in this set? counting repetition. So that's going to be equal to 9. So let's just pretend that they are all different. So that's, for example, A1, A2, A3, B1, B2, C1, C2, C3, and C4. So let's pretend they're all different temporarily. So if we rearrange all 9 objects and treat all of them as different, then how many rearrangements am I going to have? So therefore, the number of rearrangements is actually going to be equal to, and let's assume we choose all of them, so we're rearranging all of them, that's going to be equal to 9 for the first, 8 for the second, 7 for the third, 6 for the fourth, all the way down to 1 for the last, which is of course going to be equal to 9 factorial. And if you want to calculate 9 factorial, that's going to be equal to 362,880. So that's quite a big number. Now, let us now pretend that these A's are now indistinguishable and these B's are now indistinguishable, and same for the C's, right? So these permutations of these objects, for example, A1, A2, A3, is actually equal to, now we want at least, this to be equal to, for example, A2, A1, and A3. So in general, these are all pretty much equal to A, and A. So if that is the case, well, how many rearrangements of these are now the same? So how many A permutations? So how many A permutations are now indistinguishable? Indistinguishable. That is, you can't see the difference between them. So that's clearly going to be equal to 3 factorial, or 6 of them. So there's 3 factorial, or 6 different permutations of these A's that are now the same to me. Well, what about the other letters, for example, the B's? So for example, the number of B's that are now indistinguishable are 2 factorial, which is going to be equal to 2. Because I have 2 B's in here, if I rearrange them, they're going to look the same to me. And what about the C's, where there's 4 C's in that set? So the number of rearrangements of the C's that are now indistinguishable is going to be equal to 4 factorial, which is the same as 4 times 3 factorial, which is the same as 4 times 6, which is going to be equal to 24. So we have 6, 2, and 24. So originally, if we treat all of them as the same, we're going to have 9 factorial of them, but there's some repetition that we don't want to double count for. In particular, there's 6 of these A's that we don't want to count again, there's 2 of these B's that we don't want to double count for, and there's 24 of these C's that we do not want to double count for. Since the fundamental counting principle is counting everything multiplicatively, we need to divide if we want to take away the repetitions that we no longer want to count. So this is going to be equal to 9 factorial divided by 3 factorial times 2 factorial times 4 factorial. And once you work out all that math, we actually only have 1,260 rearrangements that we're actually going to be able to see the difference between. So can we actually extend this further, or maybe construct a more general formula for this type of procedure? And indeed we can. So let's see if we can do that. So in general, if there are n objects that contain, let's call it K1, K2, down to KR repetitions of the R distinct objects. So in the case above, we had 3 different distinct objects in the set, in particular A, B, and C. And the numbers 3, that's going to be, for example, K1, and 2 is going to be K2, and 4 is going to be equal to K3. So there's the repetitions of each of these distinct objects in the set. So if this is the setup that we have, then the number of distinct rearrangements of the n objects, and keep in mind this is without replacement, is what? So that's going to be equal to, now sometimes people will write this as n k1 comma k2 comma down to kr. They'll write it like this with a parenthesis, sort of like a fraction but without the bar in the middle. But this is precisely equal to n factorial over k1 factorial, k2 factorial, all the way down to kr factorial. So this is the same structure as we had before. And this actually has a fancy name to it. This is called a multinomial coefficient, which has several different applications. We'll be looking at one a little bit later. So let's look at a particular example and see if we can calculate this right quick. So consider the set S, which consists of, let's say, red, 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 red. So we have 5 people with red shirts, and we have blue, 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 so 3 people with blue shirts. Let's assume we have, let's say, green, 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 so 4 people with green shirts, and 1 person with a yellow shirt. And let's assume that the color of their shirts are the only thing that sets them apart. And you were to rearrange all of these people. So how many people do we have? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So the size of this set is going to be 13. So if we want to rearrange all of these objects, so let's assume that's the problem that we want. So rearrange all 13 objects. So if we were to treat all of them as different, then there's going to be 13 factorial different rearrangements of them. But when we rearrange these R's and these B's and these G's, we cannot see the difference between any of them. So we don't want to count all of those 13 factorial ones out. So using this multinomial formula that we've just described, the number of rearrangements is going to be equal to 13 factorial over, so it's going to be equal to 5 reds, 3 blues, 4 greens, and we can actually include that 1 yellow if we want to. So that's going to be equal to 5 factorial, 3 factorial, 4 factorial, 1 factorial, and that's actually going to come out to the very nice number, 360,360. So that's a pretty nice number. And keep in mind a very common property that you may encounter. What is 0 factorial? This is actually defined to be equal to 1. Now, why would we want to define that to be equal to 1? That's a longer story that we'll look into at another time, but for now, just take it as a definition. But this is the multinomial coefficient and some applications associated to that. Now let's look at a particular case of it. So let's assume that there are actually only 2 distinct objects among the n total objects in our sample data set S. So in this particular case, a multinomial coefficient is going to be called a binomial coefficient, and there's going to be several different occurrences of binomial coefficients that we're actually going to consider in this elementary treatment of statistics and probability theory. So let's actually look at a particular example that we're actually going to be experiencing quite a lot. So let's consider the set S that's going to contain a few letters, in particular the letters T and F. This is going to represent true and false, or successes or failures later. So let's assume we have TT, FT, FFF, T, and F. So how many T's do I have in this particular set? Well, first off, the number of elements I have total is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the number of elements of T, that's going to be equal to 4. So 1, 2, 3, and 4. So if I actually only have 2 distinct elements in the set, because the other element's just going to be equal to F, the number of F's in this particular data set is actually just going to be equal to the number of S's minus the number of T's. So it's just going to be equal to 9 minus 4, which is equal to 5. Yes, you could count that in this set directly, but this shortcut's going to be very, very useful if this data set is actually super large. Like instead of 9, it's like 900 or something like that. So the number of rearrangements of these trues or falses, or these successes or failures, is going to be equal to what? So if we go about this in the same exact way as before, if we treat all of them as different, there's going to be 9 factorial different rearrangements, but we have some repetition. In particular, we have 4 factorial and 5 factorial which is actually just going to come out to 126. So let's generalize this binomial coefficient out. So if there are k t's among the 4 or among the n total objects, then there are how many f's? So if there's k t's and n total objects, then there's going to be n minus k f's. So if that's the general case, that means the number of rearrangements of those n objects that are distinguishable from one another is going to be equal to n factorial over k factorial times m minus the k, the quantity, factorial. Now this is going to have a shorthand notation. This is going to be CNK, which is also sometimes written as NK with the parentheses with no fraction bar on top. Now, of course, this formula actually can be shown to be equal to the number of permutations divided by k factorial, but these are the general common notations and properties that you should definitely be familiar with. Again, this is called a binomial coefficient, and this is called a combination, or a combinatorial number, if you may. So there are some very special properties that we're actually going to take advantage of throughout this course. Let's just name them. We're not going to prove them, but if you're in a theoretical course, I definitely invite you to try to prove some of these. Some important analytical properties of combinations. So we have n total objects, we're choosing k of them without replacement. All right, so firstly, if n is a natural number, Cn and Cn0 are always going to be equal to 1. That should be very easy to prove. Cn1 and Cnn minus 1, this is always going to be equal to n. So some shortcut calculations. Cnk and Cnn minus k are always going to be equal to each other, so keep in mind k is between 0 and n need be a natural number. And there's one very interesting property that we will take advantage of in a couple scenarios, and that's Cnk is going to be equal to Cn minus 1k plus Cn minus 1 k minus 1. We're not going to get into the applications of these properties, but they're going to come in handy to prove some important results later. So also remember, before we get too far off, we were treating the pair AB and BA as different pairings, as different object pairs. Okay? So, how does this sort of tie into combinations? Well, actually, combinations treat these as equal. So it's a different perspective or a different conclusion that you can actually use combinations for, right? Because what were combinations? Well, it was just rearrangements of k objects selected from n total objects. Or if you have k objects from the binary set of two different objects, it was just the rearrangements of those k objects amongst its counterpart, or its complement, or its complementary object. So technically, one can show if the size of S is equal to m, and let's assume again this is n distinct objects, and you select k of them without replacement. Then, now notice how these problems are completely different, right? So for example, the problem that binomial coefficients were solving before was like A, and B. So how many rearrangements of these letters are there? So the size of S, or the rearrangements of the elements in S, which is going to be equal to 1, 2, 3, 4. So 6, choose 4. Or you could focus on the B's and do just 6, choose 2. You'll actually get the same exact answer. But notice in this assumption, we're treating all these objects as different. And we're selecting k of them. So if that is the case, we've actually already shown that if AB and BA are treated as different, then the number of rearrangements is actually equal to Pnk, or n factorial divided by n minus k, the quantity factorial. But if you treat these as the same, because they have the same letters, if that means anything to you, then the number of rearrangements actually is equal to Cnk, which is again n factorial, k factorial, n minus k factorial, right? Some people will say that, order doesn't matter here. Order doesn't matter here. And for this, people will say that order matters here. I've just found that, going about teaching this order matters, order does not matter, typically causes confusion, because notice that I have actually avoided using these two words in this entire explanation, but you may encounter those type of explanations in your journey of permutations and combinations, but combinations is definitely the more common form of it. But notice that the combination of objects actually has two different uses: selecting k objects from n distinct objects, or rearrangements of binary types of structures. So that's two different applications of combinations, which I think is very, very interesting. Now that we have these two situations spelled out for us in terms of permutations and combinations, let's see if we can break one of these assumptions. In particular, without replacement. What if we allow replacement to take place? What would these permutations and combination formulas turn into? So let's consider that. So let's assume if S is equal to N, and let's assume that all these objects are, again, distinct. So distinct objects, and you select K objects with replacement. Then, so first scenario, if AB is not equal to BA, we've actually already showed that the number of elements in the rearrangements is actually equal to n times n times n, all the way down to the kth object, which is just going to be equal to nk. So of course we can easily prove that that's not a big deal. But if A and B are defined to be equal to, or A and B and A are defined to be equal to equivalent to one another, that's pretty much the with replacement form of a combination. So one can show that the size of this relationship, and this is technically, there's several ways that you can write that. It's pretty much like combination with replacement. You can create a fancy little symbol if you want to, CRNK if you want. But if that's too complicated, some people will use NK with a double parentheses written around it. And this is actually defined to be equal to m plus k minus 1 all over k. And you can actually find that to be equal to m plus k minus 1, the quantity factorial, all over k factorial times n minus 1 factorial. So this is what we call the multi-choose, or the multi-choice of these objects n and k, because you can select the same object many times because you're replacing it back into the set. So this is combination with replacement, or multi-choice. So let's look at a particular example of this. So let's assume the set S that we're interested in selecting from collects the distinct elements A, B, C, D, E, and F. Now let's go ahead and choose 4 of them. And let's assume that replacement is allowed. And let's also assume that order doesn't make a difference in outcome. That is, AB and BA would be defined to be equal to one another. Now, why would this actually make sense in real life? Well, keep in mind, sometimes the person who finishes first will get a different reward. But if there's no difference between I finishing first and you finishing first and I coming in second or you coming in second, then that would, mean that the order doesn't really create a difference in the outcome. So that's what we're pretty much hinting at here. So if this is the case, well, how many different rearrangements of these four objects can be generated if replacement is allowed? So keep in mind, in the rearrangements, so what would our R set look like? Let's just list out a couple. So we could have A, B, C, and D. We could also have A, C, D, and F. And all of these rearrangements, so you could do like C, E, D, F, and A, and so on. Also, you could have A, and A. Now, in the original combination where replacement is not allowed, this wouldn't be possible. But when replacement is allowed, you can get, for example, A, B, B, and oh, we're only selecting four of these elements, right? So why is there a fifth element there? Yeah, so let's delete them. So then those would be allowed, which is pretty interesting. Now keep in mind, if A, B, C, and D is in this set, since order does not make a difference, that means the set B, A, D, C would not be counted in this set because that is equal to that because they contain the same exact letters. So with these assumptions, this is simply a multi-choice of 4 chosen from the original 6. So that means the number of rearrangements is going to be equal to 6 multi-choose 4. So it's going to be equal to 6 plus 4 minus 1, the quantity factorial, all over 4 factorial times 6 minus 1, the quantity factorial. And that's going to come out to 126. Now, another scenario that you may want to consider, what if repetition exists? We'll consider this problem another day. Because definitely you can see how things become a lot more complicated, but that's, for a different day. With these basic things, we can actually solve a lot of the problems. But let's take a look at one other thing that comes up in some probability problems. So let's suppose you have another set S that has n distinct objects, and let's consider some original arrangement of those n objects. Let's define it as x1, x2, down to xm. It actually doesn't really matter how you define the initial rearrangement, as long as the original rearrangement has exactly n objects in it, and they're all different. It actually doesn't matter what you define this to be. So then, the number of rearrangements of those n objects for which every object must change position. So that means x1, once you rearrange it, cannot be in this first position, x2 cannot be in the second, down to xn cannot be in position m. So all of these rearrangements are called derangements. So let's look at a couple basic examples before we actually look into the formula that we can actually calculate these outwards. So let's assume we don't know a formula. How will we do it by hand? So let's assume we have a set of 2 objects, so A and B. So how many rearrangements of objects A, B are there? Well, the number of rearrangements is of course A, B, and B, A. So these are all the rearrangements. But keep in mind the derangements do not allow A to be in position 1 and B to be in position 2. Therefore, that needs to be discarded. So that means the number of derangements of 2 objects is actually equal to 1. So let's consider a very trivial case. What about one object, say A? How many derangements of this is there? So there's actually only one rearrangement of this, and that's precisely equal to A, but A cannot be in its original position. Therefore, the derangements of one object is actually equal to 0. We define the derangements of 0 objects to be equal to 1. We're not going to get into why that is the case, but that's pretty much, it's sort of like 0 factorial equals 1 sort of thing. So if that is the case, let's look at a more larger set and see if we can figure out what all of the derangements are equal to. So let's consider the set S to be equal to A, B, C, and D. And let's assume that that is its original position. So the number of rearrangements is going to be equal to, and let's assume that this is going to be the set of all derangements. All right, so I'm just going to call it D. So we could have B, C, D, and A. We could also have B, A, D, and C, and also B, D, A, and C. Those are all of the derangements where B is in position 1. We could also move C in position 1, and we could also have D in position 1. So let's figure out all of those. So we could have C, A, D, B, C, A, B, and D. But wait a minute, you can't have D in the last position, so that wouldn't work. So what would be the others? C, D, B, and A. C, D, A, and B. So what about D in position 1? So we could have D, A, B, C. That's the obvious one. Then we could have D, C, B, and A. And lastly, D, C, A, and B. Is that all? You can take a moment to figure out that that is actually all of them. So the number of rearrangements in this particular set, let's call it D. And that's, of course, for 4 objects. We're going to be abbreviating that up by D4, is equal to 9. So what if you actually don't know if you're missing any? For example, what if I give you a set containing 50 objects and you list a lot of them? How do you know you have them all? So one can show that the formula for the nth derangement, or the derangement of n distinct objects, is actually going to be equal to the floor of n factorial all over e plus 0.5. So this symbol, the little bracket with the bottom, that just means round down. Okay, so if you see, for example, the floor of 0.3, that's going to be equal to 0. The floor of 0.5, that's going to be equal to 0. The floor of 0.9999999, that's also going to be equal to 0. Right? So what is this e then? So e, that's the exponential base of e. Maybe you saw that in pre-calculus or somewhere. That's approximately equal to 2.71828. And there's infinitely many decimals there, but that's an approximation for it. So that is the derangement of n distinct objects. So it's the number of derangements of n distinct objects. Some people will abbreviate dn by n with a factorial before it, and some people will refer to this as a sub-factorial. There's a few reasons why I don't like this notation and why I prefer the dn notation. One, it sort of confuses the factorial representation. For example, if I write 3 factorial 5, is this 3 factorial times 5 or 3 times 5 subfactorial? Right? Now, of course, one can define this to be equal to one of those, but then we're just creating too many rules to keep in mind, right? So if I write, for example, dn factorial, everyone knows what that means. And if I write dn factorial, everyone knows what that means. So there's no conflict of discussion, right? That's why I choose to use dm. So with this other example, we show that D4 is equal to 9 by listing all of them. So is it possible that we can generate that answer via this little calculation formula? And indeed the answer is yes. So D4 is going to be equal to the floor of 4 factorial divided by E plus 1/2. So one can find that that's approximately equal to the floor of 9.3291. Approximately not equal to each other, but that of course rounds down to 9, which is the same exact answer as before. Now, a couple other analytical properties of derangements that you may need in the future are the following. So just a couple notes here. So dn, the nth derangement, can actually be found in another way, n factorial times the sum from k is equal to 0 to m of negative 1 to the power of k all over k factorial. So it's an alternating sum of reciprocal factorials, which is an interesting thing. So using this, one can actually show this second property, in particular the limit, as n goes to infinity, of the nth derangement divided by n factorial, this is actually equal to 1 over e. Now, if you don't know what limits are, that's perfectly okay, but this is a fun little exercise to prove for some of you calculus people. So we've discussed several different counting techniques in this video, right? So we have permutations, combinations, repetition, with, without replacement, combinations with replacement, so multi-choices, multinomials, derangements, and there are several different things that we didn't consider here, right? So for this derangement, we assumed that we were deranging all of the n objects, and we were assuming that all of them are distinct. So is it possible we can derange a subset of objects for which there exists repetition? So a very natural question is there more variations of these topics? And the answer is, of course, yes, but this is pretty much all we're going to need, at least in the near future. If you're interested in studying these other foundations, of course, there's going to be a course for that known as combinatorics. So if you're interested, I will see you in that series. Otherwise, these calculations for counting objects is just going to be perfectly fine for our purpose in statistics and probability. So I will see you in the next video. Take care.